Afternoon, everybody. We're going to take notes on this section 5.3, which is Riemann sums and definite integrals. So we've seen indefinite integrals, and now we're going to see what a definite integral is. You don't have to write anything down yet, but just kind of listen along. This guy, George Frederick Bernard Riemann, is the guy who invented these Riemann sums, which is kind of this idea of breaking an interval into a bunch of subintervals and then finding the area of a bunch of rectangles and adding them all up. So those sums are what are called Riemann sums. German mathematician Riemann did most of his famous work in the areas of non-Euclidean geometry, differential equations, and number theory. It was Riemann's result in physics and mathematics that formed the structure on which Einstein's general theory of relativity is based. Humble, humble flex. So, definition of a Riemann sum. So, a Riemann sum is when we have a sum of n rectangles where we take the height of each rectangle times the width of each rectangle. And this is just our formula how we found area over an interval. You don't have to write this part yet, but that's what these type of sums are called Riemann sums. Again, don't have to write this yet. One idea that I want you to be aware of is that when I estimate the area under a curve, I don't necessarily need the width of each rectangle to be the exact same. If you notice, these widths are all different, but it's still going to give me an approximation. And you could still do our work here to find the area under the curve. As the number of rectangles goes to infinity, we'll still get that area under the function. So what you call the width of these intervals is called the norm, and this symbol represents the norm. And we've used a constant norm, so delta x has always been the same. That's where we just take the width of the interval divided by n. That doesn't always have to happen. We can take different width intervals. We're not going to need to, but just be aware that that's okay. And instead of thinking of this as the number of rectangles go to infinity, another way to think of it is think as the widths of these rectangles get smaller and smaller and smaller. So instead of n going to infinity, you can also think of it as the width or the norms going to 0. So that's where this definition of a definite integral comes from. This is almost exactly our definition of area under a function before. Instead of taking the number of rectangles as n goes to infinity, we're going as the width approaches 0. And we're going to take the sum of a bunch of area of rectangles. We're going to take the height and the width, multiply them together, and then sum them all up. And what we call that number is the definite integral of a function from a to b. So right here, the limit is called the definite integral of f from a to b. The number a is the lower limit of integration, and the number b is the upper limit of integration. Take a minute to pause the video and just copy this down. And additionally, theorem 5.5, the definite integral as the area of a region, we can use this to find the area if f is continuous and non-negative on the closed interval. Then the area of the region bounded by f, the x-axis, and the vertical lines at a and b is given by this symbol here. So this is how we can find the area of a function. You just take a Riemann sum from a to b and do what we've been doing. So if I were to find the area or evaluate this definite integral, the integral from -2 to 1 of 2x dx, that's equivalent to taking the limit. Now, I'm just going to use our original definition as the number of rectangles goes to infinity of a sum where I goes from 1 to n of f of ci delta x, and delta x is the width of our intervals. So delta x is b minus a over n, and we're going from -2 to 1, so that's our a and b. So it's going to be 1 minus -2 over n. All right, a to b. And that's going to be 3 over n. So we got delta x. And then to find ci, we're going to start at a and go over delta x I times. A is -2, and delta x is 3 over n. So it's going to be 3i over n. So now I got ci. So now I'm going to take the limit as the number of rectangles goes to infinity of this Riemann sum, which is f of -2 plus 3i over n times delta x, which is 3 over n. So we have the limit as n goes to infinity of the sum where I goes from 1 to n. So my function just takes its input and doubles it. So it's just going to be 2 times negative 2 plus 3i over n times 3 over n. And now let's put our algebra caps on and crank this out. So distribute the 2. So we're going to get minus 4 plus 6i over n. And we can factor that 3 over n out. So I'll put that 3 over n right here. Okay. Now I'm going to use my sum formulas. So we have 3 over n factored out. And then if I add up negative 4n times, that formula is just negative 4n. And then I have a 6 over n here. If I add up I n times, 1 plus 2 plus 3 plus all the way to n, we have that formula. N times n plus 1 over 2. Recognizing that, let's see, that n is going to eliminate that n, and 6 divided by 2 is 3. So now I have the limit as n approaches infinity of 3 over n times negative 4n plus, now I have a 3 times n and a 3 times 1. So it's going to be plus 3n plus 3. We got like terms here. So this is really just negative 1n plus 3. So I'm going to distribute that 3 over n in here. And so now I have the limit as n goes to infinity. Let's see, 3 over n times negative 1n is going to give me negative 3n over n. The n's are going to cancel out. And 3 over n times 3 is going to give me 9 over n. And so this is going to give me negative 3 plus, as n goes to infinity, this is going to be 0. So I just get negative 3. So that is how we can evaluate a definite integral. If you put this in the calculator, it turns out that it equals negative 3. Now, let's look at this from an area perspective. The function is 2x. And we're looking at the area under the curve from negative 2 to positive 1. So I want to find the region bounded by the function. The vertical lines, x equals negative 2 and x equals 1, and the x-axis. What I'm looking for is this area here. Now, when we have area under the x-axis, we're going to think of it as area, but it's going to be a negative value. So the area of this section is a triangle, so it's 1/2 base times height. The base is 1. The height is, well, if I plug 1 into the function 2x, 2 times 1 is 2. So the area of that region is 1/2 times 1 times 2, which is 1. The area of this region here is going to be 1/2 times the base. The base is 2. The height down here, if I plug negative 2 into this, I'm going to get negative 4. So this kind of height right here is negative 1, 2, 3, 4. And that's going to give me a 4. But because it's below the x-axis, we have to recognize that this is really a negative area. So think of it as a negative 4. And if I want to find the area between the curve from negative 2 to 1, I got to add the 1 and the negative 4. And that's going to give me negative 3. That's exactly what we got over here. So what we're going to do today is look at evaluating integrals, but without doing this, we're going to do it using an area argument. Of course, this won't work for curved shapes other than circles, but I want to train us to think about it like an area problem. So copy this example down. We're going to sketch the region corresponding to each definite integral and then evaluate it using geometric formulas. So this right here is asking me what's the area of the function 4 from 1 to 3. So from 1 to 3, I want to graph the function, the constant function 4. So y equals 4 looks like this. So between 1 and 3, this representation represents the area of this region of the graph. So to find that area, it's just base times height. The base is 2, and the height is 4. Right, so it's 2 by 4. So that's going to give us 8. So that means this is equal to 8. Without having to do an infinite sum or a Riemann sum, the geometry kind of makes it a little bit simpler. Now on this one right here, we're looking for the region bounded by the function x plus 2. So that's going to start at 2. And we're going from 0 to 3. 3. So this is a linear function that starts at 2. If I were to find out what the value is at 3, just plug in 3, and 3 plus 2 is 5. 4, 5. So this is the function x plus 2 approximately. And we want to find the area under that curve from 0 to 3. So I want to find the area of this region right here. I'm going to break it up into a rectangle and a triangle. If you want to use a trapezoid formula, feel free. So the area of this region right here is base times height. The base is 3. The height is 2. So that area is 6. The area of this triangular region, it's a right triangle, so that's going to be 1/2 the base times the height. The base is 3. And the height, it's going from 2 all the way up to 5, so that height is also 3. 3 times 3 is 9. Half of 9 is 4.5. So if you want the area under the curve, it's going to be whatever 4.5 plus 6 is, which is 10.5. So again, we don't have to break this up into infinite rectangles. We can get the area by just using nice geometry formulas. And now we're going to do the same thing here. You might not recognize what this graph is, but the graph, it's going to be the graph of a half a circle. So a circle is going to be y equals r squared minus x squared. This is actually half of a circle. This is the top half. So if you want a full circle, you need to have plus or minus. The minus would be the bottom half. So you can think of this as 2 squared. So the radius, this is a circle with a radius of 2. And this is actually centered at the origin. So if I were to sketch that, oops. It's centered at the origin with a radius of 2. So here is my semicircle. And all we're asking to do is find the area bounded by the region, x equals 2 and x equals 3. So the area is just going to be half of a circle, so that's half of pi r squared. And the radius is 2. So that's going to be half of 4 pi, which is 2 pi. So this is equal to 2 pi. And that's how we can evaluate some definite integrals without doing that long Riemann sum where we have a limit as n goes to infinity of an infinite sum of a sum of rectangles. Okay, copy down these two definitions of special definite integrals. If f is a definite integral at x equals a, then we write the integral from a to a of a function is always 0. Think of this as if the width starts at a and ends at a, there is no width. So the area of that region is always going to be 0. And if I switch a to b to b to a, you can always flip these limits of integration. And if you do that, then you just change the sign of the value to a negative. Or if it's already a negative, you make it positive. So if you flip the limits of integration, you just have to change the sign. So if I ask what's the area under the curve of the function sine of x from pi to pi, again, if you're going from the same value to the same value, there's no width. That's just going to be 0. Now, if I wanted the area under the curve of the function x plus 2 from 0 to 3, that's equivalent to switching this from 0 to 3 now of negative, or making it negative, x plus 2 dx. Now, this we actually already did up here. I think we got 10 and a half. So this is really just 10 and a half. So what that implies that the answer to this integral, or the value of this integral, is going to be negative 10.5. Okay. All right. Additive interval property. If the function is integrable on 3 closed intervals determined by a, b, and c, then if I want the integral under a function from a to b, I can go from a to c, take that section, add that to the section from c to b, and that'll give me the area under the full curve. So here's an example why that might be useful. The absolute value of x looks like this. Now I want to look at this function from -1 to 1. If you plug -1 in, you get 1. If you plug +1 in, you get 1. So the area between -1 and 1, I can break it up and go from -1 to 0 first. Find that chunk. And this function right here is negative x. Then I could add, right, that's what I'm using this property right here, the integral from 0 to 1 of this function, which is positive x, and then find that area and add it up. So the area of this is a triangle, so it's going to be 1/2 the base, which is 1, times the height, which is 1. So that area is 1/2. This one I bet is going to be the same thing. It's 1/2 times base times height. The base is still 1, and the height is still 1. So that's also equal to 1/2. So this is just adding 1/2 plus 1/2, which is 1. Okay. A simple example geometrically, but this is a generally true, not just for simple absolute value functions. Right, and the last property we're going to copy down is that if you have two functions on an integral and there might be some constant that the function is being multiplied by, if you have a function being multiplied by a constant, you can factor that out of the integral. And if you're taking an integral of a sum of functions, you can just take the sum of the integral of each function. And I'm going to use this example here to illustrate those two properties. Again, copy that down. So we're asked to evaluate the definite integral of this function from 1 to 3 using this is the given information that we're going to use. So I'm going to use that first property that says I can take a sum of functions and break it up into an integral of a sum as a sum of two integrals. Even though I have 3 here, I'll just break it up into 3. So I'm going to break it into my first function plus the integral from 1 to 3 of my second function minus the integral from 1 to 3 of my third function. Now, I know the integral of x squared from 1 to 3 is 26 over 3, but I have a negative here. And I also know what the integral from 1 to 3 of x is, but I have a 4 here. So what I'm going to do is I'm going to factor those out using this constant idea. So factoring out the constant, that's going to be negative integral from 1 to 3 of x squared. Plus, I'm going to factor the 4 out. So it's going to be 4 times the integral from 1 to 3 of x dx. And I'm going to factor that 3 out so that I can just have the dx in there. And now I know that this value is just 26 thirds. This is going to give me negative 26 thirds. And then we have plus 4 times this integral we're given is equal to 4 minus 3 times this integral right here is equal to 2. So This just becomes negative 26 thirds plus 16 minus 6. 16 minus 6 is 10. Or 16 minus 6 is, yeah, positive 10. Negative 26 thirds plus 10. I'm just going to rewrite this, multiply top and bottom by 3. This is really just 30 thirds. So negative 26 thirds plus 30 thirds is going to give me 4 thirds. And that's all. If you like the video, make sure to share with your friends. Ring the bell for notifications if you're interested. And if you're not subscribed yet, please consider subscribing. It'll really help the channel so we can bring more content like this to you. Have a good one.